let me tell you about something that haunts the scientists who analyzed the data so strange, so unexpected, so contrary to everything we thought we knew about Saturn, that it has forced us to confront the limits of our understanding. In September 2017, the Cassini spacecraft plunged into Saturn's atmosphere, transmitting data until the very end. What it recorded in those final moments defies explanation. Its final message was terrifying. Not terrifying in the sense of danger or threat, terrifying in the way that the unknown is terrifying, the recognition that something fundamental about our understanding is wrong, terrifying in the way that challenges to basic assumptions are terrifying the realization that a world we thought we understood is stranger than we imagined. Cassini spent 13 years orbiting Saturn, studying the planet, its rings, and its moons in unprecedented detail. It revolutionized our understanding of the Saturnian system. And then, running low on fuel, it was deliberately plunged into Saturn's atmosphere to prevent any chance of contaminating potentially habitable moons like Enceladus. In its final hours and minutes, Cassini performed one last act of science, diving between Saturn and its rings, skimming through regions no spacecraft had ever visited, and finally plunging into the atmosphere itself. The data it collected in those final moments was transmitted back to Earth, arriving hours after the spacecraft had already been vaporized. And that data contained mysteries we still cannot explain. Let me take you through what Cassini found, because understanding it requires appreciating both the extraordinary mission that preceded it and the profound strangeness of what was discovered at the end. Let me start with Cassini's journey to Saturn. Cassini launched on the 15th of October, 1997, from Cape Canaveral, Florida. It was one of the largest and most complex interplanetary spacecraft ever built, nearly 6 tons at launch, carrying 12 scientific instruments and the Huygens probe, which would later land on Saturn's moon Titan. The journey to Saturn took nearly 7 years. Cassini used gravity assists from Venus twice, Earth and Jupiter, to gain the velocity needed to reach the outer solar system. It was a cosmic billiard shot, using the gravitational fields of multiple worlds to fling itself toward its distant destination. On the 1st of July 2004, Cassini arrived at Saturn. It fired its main engine for 96 minutes, slowing itself enough to be captured by Saturn's gravity for the first time. A spacecraft entered orbit around Saturn. What followed was 13 years of discovery, one of the most scientifically productive missions in the history of space exploration. Cassini revealed Saturn's rings in unprecedented detail, showing structure and dynamics we never imagined. It discovered new moons and watched the rings interact with existing moons in complex gravitational dances. It observed storms that dwarfed anything on Earth, including a massive hexagonal vortex at Saturn's North Pole that has persisted for decades. The mission discovered that Enceladus, a small icy moon, harbors a global subsurface ocean that vents into space through cracks near its south pole. These geysers contain water, organic molecules, and the chemical ingredients for life. Enceladus became one of the most promising places in the solar system to search for extraterrestrial life. Cassini deployed the Huygens probe, which landed on Titan in January 2005, the first landing ever achieved in the outer solar system. Huygens revealed a world eerily reminiscent of Earth. Lakes and rivers of liquid methane, rain and weather cycles, complex organic chemistry, and a thick atmosphere that hides the surface from view. For 13 years, Cassini orbited Saturn, making discoveries that filled scientific journals and rewrote textbooks. But all missions must end. And Cassini's ending would become one of the most scientifically valuable parts of the entire mission. Now let me describe the grand finale. As Cassini's fuel dwindled, mission planners faced a decision. They could allow the spacecraft to drift uncontrolled, eventually crashing into one of Saturn's moons. But this posed a contamination risk. The spacecraft built on Earth might carry microbial hitchhikers that could compromise future searches for life. Instead, they chose to dispose of Cassini in Saturn itself. The planet's immense atmosphere would vaporize the spacecraft completely, eliminating any contamination risk. And the death dive would provide unique scientific opportunities. The grand finale began in April 2017. Cassini performed a series of 22 daring orbits, diving between Saturn and its innermost ring, a region never before explored by any spacecraft. Each orbit brought Cassini closer to the planet, skimming through the gap where the inner ring meets the upper atmosphere. These orbits were risky. The region was unexplored. Mission planners couldn't be certain what hazards might lurk there. Ring particles, even small ones, could damage or destroy the spacecraft at orbital velocities. But the potential for discovery outweighed the risks. Cassini survived all 22 orbits, returning data that would reshape our understanding of Saturn. And then came the final plunge. On the 15th of September 2017, Cassini entered Saturn's atmosphere for the last time. There would be no escape. The spacecraft would continue deeper until friction and pressure destroyed it. But until that moment, it would keep transmitting, sending back data from regions no instrument had ever measured. The last signal from Cassini arrived at Earth at 7:55 a.m. Eastern Time. By then, the spacecraft had been dead for 83 minutes, the time it took for the final transmission to cross the gulf between Saturn and Earth. What that final transmission contained was extraordinary, and parts of it remain unexplainable. Now let me discuss what Cassini measured in its final moments as Cassini dove into Saturn's atmosphere. Its instruments measured everything they could: atmospheric composition, density, temperature, magnetic field strength, charged particle populations, and more. The data streamed back to Earth, painting a picture of an environment never before directly sampled. The first surprise involved Saturn's atmospheric composition. The standard model of giant planet atmospheres predicted that Saturn, like Jupiter, would have an atmosphere dominated by hydrogen and helium in roughly cosmic proportions, about 75% hydrogen and 24% helium by mass, with trace amounts of other compounds. Cassini's measurements showed something different. The helium fraction in Saturn's upper atmosphere was significantly lower than expected, and the distribution of other elements was strange. This wasn't entirely unexpected. Previous remote observations had suggested helium depletion in Saturn's upper atmosphere. The leading explanation involves helium rain, the idea that helium, under the immense pressures deep within Saturn, becomes immiscible with hydrogen and sinks toward the core as liquid droplets. But the degree of depletion and the distribution of other elements didn't match the models. Something about Saturn's atmospheric dynamics was different from our predictions. More puzzling were the trace compounds. Cassini detected molecules that shouldn't exist in the proportions observed, compounds that should have been destroyed by Saturn's atmospheric chemistry or should have sunk to lower levels. Their presence suggested circulation patterns or chemical processes we don't understand. Now let me describe the magnetic field anomalies. Saturn has a powerful magnetic field generated by dynamo action in its deep interior, where hydrogen is compressed into a metallic state. This magnetic field shapes the space environment around Saturn, trapping charged particles, influencing ring dynamics, and interacting with the solar wind. Before Cassini, we had measured Saturn's magnetic field from flyby missions, Pioneer 11, Voyager 1 and 2. But these were brief encounters, providing snapshots rather than continuous monitoring. Cassini spent 13 years measuring Saturn's magnetic field from orbit, and in its final dives, it measured the field closer to the planet than ever before. What it found was disturbing. Saturn's magnetic field is uniquely symmetric. Unlike Earth, Jupiter, or any other magnetic planet, Saturn's magnetic axis is almost perfectly aligned with its rotation axis. The magnetic poles are essentially at the geographic poles. There's almost no tilt. This is theoretically problematic. Dynamo theory, our understanding of how planetary magnetic fields are generated, suggests that perfectly axially symmetric fields should not exist. The mathematical theorems that govern dynamos seem to forbid them. Some asymmetry, some tilt should be present. Yet Saturn's field is symmetric too within measurement precision. Cassini's close passes confirm this, pushing the upper limit on any tilt to less than 0.01 degrees. How can this be? We don't know. The theories that explain every other planetary magnetic field fail for Saturn. Something is different about Saturn's interior, something that generates a magnetic field that shouldn't exist, according to our understanding of physics. But there was something else, something even stranger. In its final orbits and final plunge, Cassini detected fluctuations in the magnetic field that didn't match any predicted source. Brief variations, lasting seconds to minutes, that appeared and disappeared without clear pattern. At first, scientists attributed these to instrument noise or spacecraft motion. But careful analysis ruled out these explanations. The fluctuations were real. They came from Saturn. What could cause magnetic field fluctuations on these timescales? The dynamo process operates deep within Saturn and changes slowly over years or decades, not seconds. The solar wind can affect the outer magnetosphere but shouldn't penetrate to the depths Cassini was measuring. Ring particles carry small currents but not enough to produce the observed effects. The fluctuations remain unexplained. They suggest processes occurring within Saturn that we have not identified magnetic dynamics that our models do not capture. Now let me discuss what Cassini found about Saturn's interior. One of the grand finale's primary goals was to measure Saturn's gravitational field with unprecedented precision. By tracking small changes in Cassini's velocity as it swooped close to the planet, scientists could map the distribution of mass inside Saturn. What they found was surprising. Saturn's interior is not what we expected. The standard model predicted a small, rocky core surrounded by layers of metallic hydrogen, molecular hydrogen, and finally, the visible atmosphere. The transitions between layers were thought to be relatively abrupt. Cassini's gravity measurements told a different story. The distribution of mass suggests that the transitions are fuzzy, that there isn't a clear boundary between core and envelope, but rather a gradual change. The core appears to be diluted, with heavy elements mixed upward into the surrounding hydrogen, rather than concentrated at the center. This has implications for how Saturn formed and evolved. A diluted core suggests different formation processes or subsequent mixing that altered the original structure. It challenges our models of giant planet formation and evolution, but more puzzling was the rate of rotation. Saturn rotates faster than any other planet in the solar system. A day on Saturn lasts only about 10.5 hours. But determining exactly how fast has been surprisingly difficult. For most planets, the rotation rate can be measured by tracking surface features, but Saturn has no solid surface. It's a fluid body with bands, storms, and cloud patterns that move at different speeds depending on latitude. There's no fixed landmark to track. An alternative is to measure the rotation of the magnetic field. Since the field is generated in the deep interior, it should reflect the rotation of the core. For Jupiter, this works well. Jupiter's magnetic field has a clear tilt, and tracking the magnetic pole's rotation gives a precise rotation rate. But Saturn's field is symmetric. There's no magnetic feature to track. The magnetic pole doesn't visibly rotate because it's aligned with the rotation axis. Cassini tried to determine the rotation rate through other means, measuring periodicities in the magnetic field, in radio emissions, in the motion of the rings. Different methods gave different answers, varying by several minutes. This shouldn't happen. Saturn has a single rotation rate, the rate at which its deep interior spins. All methods should converge on the same value, but they don't. The discrepancies persist. In its final measurements, Cassini provided the most precise data yet, but the mystery deepened rather than resolved. The rotation rate of Saturn's core remains uncertain by minutes, an astonishing fact for a planet we've been studying for centuries. What is going on inside Saturn? Why can't we pin down something as basic as how fast it rotates? Now let me describe what happened in the final minutes. As Cassini descended into Saturn's atmosphere, atmospheric density increased. Drag forces grew. The spacecraft began to heat up and tumble. To maintain its antenna pointing at Earth, Cassini fired its attitude control thrusters. But the thrusters were small, designed for minor adjustments in the vacuum of space. Against the growing atmospheric forces, they were increasingly inadequate. The spacecraft fought to keep transmitting. For as long as possible, it maintained attitude control and sent data home. But the end was inevitable. About a minute before loss of signal, Cassini's data began to show anomalies. Not instrument failures. The instruments were still working, but the readings themselves became strange. The mass spectrometer sampling the atmosphere detected molecules that shouldn't have been present at that altitude. Complex hydrocarbons, typically found much deeper in the atmosphere, appeared in the tenuous upper layers. It was as if material from the deep atmosphere was somehow reaching the heights. The magnetometer recorded a sudden spike in field strength, brief but intense, unlike anything seen before. The spike lasted only seconds, then subsided. What caused it? Nothing in our models predicts such behavior. The plasma spectrometer detected a burst of charged particles, energetic ions that seemed to come from below, from the atmosphere itself, rather than from the space environment above. The source of these particles is unknown, and then in the final seconds before loss of signal, the temperature sensors recorded something strange. Instead of a smooth increase in temperature as Cassini descended into denser atmosphere, there was a brief drop, a momentary cooling where warming was expected. This made no physical sense. Atmospheric entry should produce continuous heating as friction converts kinetic energy to thermal energy. A cooling signature implied either an instrument glitch or something very unusual happening in the atmosphere. Then the signal stopped. Cassini was gone. The final data streamed back to Earth and into the waiting computers of mission control. Scientists began analyzing it immediately, and the more they analyzed, the more puzzled they became. Now let me explain why these final measurements are so problematic. The anomalies in Cassini's final data don't fit our models of planetary atmospheres. They suggest processes or phenomena that we haven't accounted for. Consider the complex hydrocarbons detected at high altitude. In the standard model, these compounds form in Saturn's deep atmosphere through chemical reactions at high pressure and temperature. They should be confined to lower levels, unable to reach the rarefied heights where Cassini detected them. For them to be present where Cassini found them, some mechanism must transport them upward, powerful convection, perhaps, or some other mixing process. But the atmospheric models don't predict convection strong enough to do this. The compounds shouldn't be there. Alternatively, the compounds might form in situ at high altitude through processes we haven't considered. But what processes? The energy and conditions at high altitude don't seem sufficient for the chemical reactions that produce these compounds. Or the detection might be wrong, a misinterpretation of the mass spectrometer data. But the instrument was well calibrated and the signatures were clear. The detection appears to be real. Consider the magnetic field spike. Planetary magnetic fields don't normally produce short-duration spikes. The dynamo process operates steadily. The field changes slowly. A spike lasting seconds implies a localized, rapid event, something releasing magnetic energy quickly. On Earth, magnetic spikes can occur from lightning or from reconnection events in the magnetosphere. Could Saturn have atmospheric lightning powerful enough to produce the observed spike? Possibly, but Cassini detected many lightning storms during its mission, and none produced magnetic signatures like this. Could there be reconnection events occurring deep within Saturn's atmosphere? This would require magnetic field structures we haven't predicted, concentrations of field energy that can suddenly release. What creates these structures? Why would they exist? Consider the burst of energetic particles. In space, particle acceleration usually occurs in electric and magnetic field structures, shock waves, reconnection regions, radiation belts. These exist in Saturn's magnetosphere, but Cassini was inside the atmosphere when it detected this burst. For energetic particles to be produced within the atmosphere itself, some acceleration mechanism must operate there. Lightning could accelerate particles, but the energies observed were higher than lightning typically produces. Some other process must be at work. Consider the temperature drop. This is perhaps the most puzzling observation. Atmospheric entry is a well-understood process. Kinetic energy converts to heat, temperature rises, a cooling signature violates basic thermodynamics unless something absorbs energy, unless some endothermic process operates, unless the instruments were measuring something other than air temperature. What could absorb energy during atmospheric entry? We don't know. What endothermic processes could operate at those conditions? We don't know. What could the temperature sensors have been measuring if not air temperature? We don't know. These anomalies individually might be dismissed as instrument quirks or data glitches, but together they paint a picture of something happening in Saturn's atmosphere that we don't understand, processes operating at levels and scales we haven't considered. Now let me discuss the scientific response to these findings. When confronted with anomalous data, scientists follow a standard process. First, verify the data, check for instrument errors, processing mistakes, or contamination. Second, seek conventional explanations. Look for known processes that might account for the observations. Third, if conventional explanations fail, consider unconventional ones. For Cassini's final data, the first step has been completed. The data has been verified. The anomalies are real, not artifacts. The instruments were functioning correctly until the moment of signal loss. The strange readings reflect actual measurements, not errors. The second step is ongoing. Scientists are searching for conventional explanations. Can the complex hydrocarbons be explained by unusually strong convection? Can the magnetic spike be explained by some feature of Saturn's magnetic field we hadn't mapped? Can the particle burst be explained by a thunderstorm or some other atmospheric phenomenon? For each anomaly, conventional explanations have been proposed. For each, problems remain. The explanations require stretching models in uncomfortable ways, invoking processes at intensities or scales we have no other evidence for. They work, but just barely, and skeptics remain unconvinced. The third step, considering unconventional explanations, is controversial. Scientists are cautious about invoking new physics or unknown phenomena. Extraordinary claims require extraordinary evidence, and while Cassini's final data is certainly unusual, it may not rise to the level of demanding entirely new explanations. But the data haunts those who analyze it. Something happened in those final minutes that we don't understand. Something about Saturn is different from our models. Something is going on that we haven't anticipated. In part 2, I want to explore the deeper mysteries of Saturn that Cassini revealed not just in its final moments, but throughout its 3-year mission. What did Cassini discover about Saturn's rings, its moons, its internal structure? And how do these discoveries connect to the unexplainable observations at the end? So we've established what Cassini found in its final moments: the atmospheric anomalies, the magnetic field spike, the energetic particles, the inexplicable temperature drop. We've seen how these observations challenge our understanding of Saturn and resist conventional explanation. Now I want to place these final mysteries in context. Throughout its 3-year mission, Cassini revealed that Saturn is far stranger than we imagined. The final anomalies are not isolated puzzles. They are the culmination of discoveries that collectively paint a picture of a world we don't fully understand. Let me take you through what Cassini found during its years at Saturn, because these discoveries set the stage for the terrifying final message. Let me start with Saturn's rings. The rings of Saturn are one of the most recognizable features in the solar system: vast sheets of ice and rock, orbiting the planet in intricate patterns. From Earth, they appear as smooth, continuous structures. Up close, Cassini revealed something far more complex. The rings are not uniform. They contain thousands of distinct ringlets, gaps, waves, and structures. Some of these are explained by gravitational interactions with Saturn's moons. Others remain mysterious patterns that appear and disappear, structures that form and dissolve, dynamics that our models struggle to reproduce. Cassini discovered that the rings are far more active than expected. Material constantly migrates between rings, falls into Saturn's atmosphere, and is ejected into space. The rings are not static. They are dynamic, evolving structures. Most surprisingly, Cassini found that the rings might be young. The standard assumption was that Saturn's rings formed with the planet itself 4.5 billion years ago. But Cassini's measurements suggested otherwise. The mass of the rings is lower than expected, and they are cleaner, less contaminated with dark material than they should be if they were ancient. The data suggests the rings might be only 100 million years old, a cosmic eye blink. If true, the rings formed long after the dinosaurs went extinct, long after complex life existed on Earth. Saturn might have acquired its famous rings relatively recently. What created them? The leading hypothesis is that a moon or comet wandered too close to Saturn and was torn apart by tidal forces. Its debris spread into the ring system we see today. But this raises questions. Why did this happen so recently? Was it a random event, or does something about Saturn's gravitational environment make such events more likely? Could it happen again? The young rings hypothesis remains controversial. Some scientists challenge the interpretation of Cassini's data, but if correct, it means that the Saturn we see today with its spectacular ring system is not the Saturn that existed for most of the solar system's history. We are witnessing a temporary state, a phase that will eventually end as the rings dissipate. Now let me discuss the rain from the rings. One of Cassini's most unexpected discoveries was ring rain material from the rings constantly falling into Saturn's atmosphere. The rings are made of ice particles, ranging from microscopic grains to house-sized chunks. These particles interact with sunlight, with Saturn's magnetic field, and with charged particles in the environment. The interactions can charge the particles electrically, and Saturn's magnetic field can then drag them along field lines into the atmosphere. Cassini found that this process removes material from the rings far faster than expected. The rings are losing mass at a rate that would deplete them entirely within 300 million years, possibly much less. This supports the young rings hypothesis, but raises additional questions. If ring rain has always occurred at the current rate, the rings couldn't have existed for billions of years. Either the process is accelerating, or the rings are indeed young. But the ring rain also affects Saturn's atmosphere. The infalling material carries water, organic compounds, and other substances into the upper atmosphere. This influx changes the atmospheric chemistry in ways we hadn't anticipated. Some of the complex hydrocarbons Cassini detected in its final plunge might have originated in the rings. Material falling from above rather than rising from below could explain their presence at high altitudes. But this doesn't fully solve the puzzle. The quantities detected were larger than ring rain alone could explain. Something else must be contributing. Now let me examine Saturn's mysterious hexagon. At Saturn's north pole, there is a hexagon. Not a vague hexagonal shape, not an approximate six-sided pattern, a precise geometric hexagon, 30,000 kilometers across, with straight sides and sharp corners. It has persisted for at least 40 years, since Voyager first observed it in 1981. It might be much older. We simply don't have observations from before. Nothing like this exists anywhere else in the solar system. No other planet has a polygonal polar vortex. The hexagon is unique to Saturn. What creates it? The leading explanation involves atmospheric fluid dynamics. When a jet stream circles a central vortex at specific velocities, standing waves can form. Under the right conditions, these waves can produce polygonal patterns. Laboratory experiments have reproduced hexagonal patterns in rotating fluids. The physics is understood in principle, but the specific conditions required, the jet stream velocity, the vortex rotation rate, the atmospheric parameters, must be precisely tuned. Saturn's atmosphere just happens to have these conditions, apparently stable for decades or longer. Is this a coincidence? Or does Saturn's atmosphere have some property that naturally produces hexagonal structures? Are there processes that drive the system toward this configuration? Cassini studied the hexagon extensively. It found that the hexagon extends deep into the atmosphere, much deeper than expected, and that its color has changed over the mission from blue-gray to golden. The color change is attributed to photochemistry as Saturn's seasons progress, but the deep structure remains unexplained. In its final orbits, Cassini passed directly over the hexagon multiple times. The data revealed internal structure, smaller vortices within the hexagon's walls, waves propagating along its edges, dynamics that operate on multiple scales. But the fundamental question remains, why does Saturn, and only Saturn, have a hexagon at its pole? What is special about Saturn's atmospheric dynamics that creates and maintains this unique feature? Now let me discuss the storm. Saturn is a stormy world. Its atmosphere contains bands of clouds, zones of rising and falling gas, and vortices ranging from small eddies to planet-spanning disturbances. Cassini observed many storms, but one stood out: the Great White Spot of 2010 to 2011. Great white spots are massive storms that erupt periodically in Saturn's atmosphere roughly once every 30 Earth years, approximately once per Saturn year. They start as small disturbances but can grow to encircle the entire planet within weeks. The 2010 storm was the first observed from orbit. Cassini had a front row seat as the storm erupted, grew, and eventually wrapped around the planet before dissipating months later. What Cassini found was shocking. The storm punched through Saturn's upper atmosphere and reached far deeper than expected, hundreds of kilometers down into regions with pressures comparable to Earth's ocean depths. The energy released was immense, equivalent to multiple times Earth's annual energy consumption. Most disturbing was what the storm brought up from below. The atmosphere of Saturn's deep interior is hidden from view, buried under hundreds of kilometers of cloud. Direct observation is impossible. We can only infer what lies beneath from theory and indirect measurements. The great white spot acted as a window into the depths. Material from below was dredged up by the storm and spread into the upper atmosphere. Cassini analyzed this material and found compounds that shouldn't exist in the quantities observed. Phosphine, a toxic gas associated with biology on Earth, was detected in abundance. Phosphine can be produced by non-biological processes at high temperature and pressure, but its presence in the upper atmosphere, brought up by convection, suggested conditions below that our models hadn't predicted. Ammonia distribution was also strange. The storm seemed to reveal pockets of ammonia-enriched and ammonia-depleted gas, suggesting inhomogeneous mixing in the deep atmosphere. Saturn's interior might be more structured, more complex than the well-mixed model assumed. What else lies in Saturn's depths? What other compounds, what other structures, what other processes operate in regions we cannot see? The great white spot provided a glimpse, but only a glimpse. The full picture of Saturn's interior remains hidden. Now let me turn to Saturn's moons, beginning with Enceladus. Enceladus is a small moon, only 500 kilometers in diameter. Before Cassini, it was considered geologically dead, an inert ball of ice. Cassini proved this spectacularly wrong. In 2005, Cassini flew past Enceladus and detected something astonishing. Jets of water vapor and ice particles erupting from the moon's south polar region. Enceladus was geologically active, venting material into space through cracks in its icy surface. Subsequent observations revealed the source: a global subsurface ocean, liquid water trapped beneath the ice shell, heated by tidal forces as Enceladus is squeezed by Saturn's gravity. The jets contain not just water, but a rich chemistry, organic molecules, silica nanoparticles suggesting hydrothermal activity, molecular hydrogen that could serve as an energy source for life. Enceladus has water, energy, and chemistry. It has the ingredients for life. This was one of Cassini's most important discoveries. A small frozen moon in the outer solar system has conditions potentially suitable for life. The search for extraterrestrial life, previously focused on Mars and Europa, now includes Enceladus as a primary target. But the discovery also raised questions. How can such a small body maintain a global ocean? The tidal heating required seems excessive for Enceladus's orbit. The ice shell should freeze entirely within millions of years unless heat is supplied faster than models predict. Some process is keeping Enceladus warm that we don't fully understand. Perhaps the interior has unusual composition or structure. Perhaps the tidal heating is more efficient than calculated. Perhaps there are heat sources we haven't considered. Cassini could not resolve this question. It observed the consequences of the heating, the jets, the ocean, the activity, but the mechanism remains unclear. And there was something else. In its close passes over Enceladus's jets, Cassini detected substances that shouldn't have been present in the abundances observed. Complex organic molecules, methane, molecular hydrogen, all in quantities that suggest active chemistry below the surface. Is this chemistry biological? We cannot say. The compounds detected are consistent with biology but can also be produced abiotically. Distinguishing between the possibilities requires closer study missions that can sample the jets directly or even penetrate the ice and reach the ocean below. But the possibility haunts the data. Something is happening beneath Enceladus's surface. Something is producing these compounds. What is it? Now let me discuss Titan. Titan is Saturn's largest moon, larger than Mercury, with a thick atmosphere that hides its surface from visible light. Before Cassini, Titan was one of the most mysterious objects in the solar system. Cassini, with its radar and infrared instruments, penetrated the haze and revealed Titan's surface for the first time. What it found was a world eerily similar to Earth. Titan has lakes and seas, but filled with liquid methane and ethane, not water. It has rivers that carve channels through icy bedrock. It has rain, methane rain, that falls from the orange sky and feeds the hydrological cycle. Titan has sand dunes built from organic particles that drift across the surface. It has mountains of water ice, hard as rock in Titan's frigid conditions. It has a complex atmospheric chemistry that produces organic compounds raining down onto the surface. In many ways, Titan is more Earth-like than any other body in the solar system, despite being utterly alien in composition. The same physical processes that shape Earth, erosion, deposition, weather cycles, operate on Titan, but with different materials. The Huygens probe, released from Cassini, descended through Titan's atmosphere in January 2005 and landed on the surface. It transmitted for about 90 minutes before falling silent, returning images and data from another world. Huygens found a surface littered with rounded ice pebbles, smoothed by flowing liquid, just as river rocks on Earth are smoothed by water. It detected methane humidity increasing as it descended, suggesting recent rainfall. It measured winds, temperatures, and pressures that confirmed Titan as an active, dynamic world. But Titan also presented puzzles. The atmosphere contains methane, but methane is destroyed by sunlight over geological time. Without replenishment, Titan's methane should have disappeared billions of years ago. Something is replenishing it, volcanic outgassing, perhaps, or release from a subsurface reservoir. Cassini searched for evidence of cryovolcanism, volcanoes that erupt water and ammonia instead of molten rock. Some candidate features were identified, but none definitively confirmed. The source of Titan's methane remains uncertain. The surface chemistry is also strange. The organics produced in the atmosphere should accumulate over time, burying the surface in deep layers of organic sediment, but some regions appear surprisingly clean. Where did the organics go? Are they processed into other compounds, buried beneath the surface, consumed by unknown processes? And then there's the question of life. Titan has organic chemistry in abundance, more hydrocarbons on its surface than all of Earth's oil reserves combined. It has liquid on its surface. It has energy sources, chemical gradients, tidal heating, possibly hydrothermal activity in a suspected subsurface water ocean. Could life exist on Titan? Not life as we know it. The conditions are too cold for liquid water, the chemistry too different. But some scientists have proposed exotic life forms that use liquid methane as a solvent, that metabolize acetylene and hydrogen, that operate on principles entirely different from terrestrial biology. Cassini could not test these hypotheses directly, but it found that hydrogen and acetylene near Titan's surface are depleted relative to predictions, as if something were consuming them. This is not evidence of life. Chemical processes we don't understand could produce the same signatures, but the depletion is unexplained, and the possibility of exotic life cannot be ruled out. What is happening on Titan? What consumes the hydrogen and acetylene? What replenishes the methane? What processes operate in that alien chemistry? Now let me return to Saturn itself and the deepest mystery of all. Throughout its mission, Cassini measured Saturn's magnetic field from orbit. In its final orbits, it measured the field from unprecedented proximity. The data revealed something that should not exist. I mentioned earlier that Saturn's magnetic field is perfectly axially symmetric, aligned with the rotation axis to within 0.01 degrees. This violates dynamo theory, which predicts that perfectly symmetric fields cannot be sustained, but Cassini found something else. The field isn't just symmetric, it's evolving in ways we don't understand. Comparing Cassini's final measurements to earlier observations, scientists found that the field had changed. The overall strength was similar, but subtle features had shifted. The rate of change was faster than dynamo theory predicts. Magnetic fields generated by planetary dynamos should be stable over thousands of years. They can change Earth's field reverses every few 100,000 years, but the changes are slow and predictable. Saturn's field changes faster. The shifts Cassini detected occurred over years, not millennia. Something in Saturn's interior is evolving rapidly, far more rapidly than our models allow. What could cause this? Internal restructuring movements of material within Saturn could affect the dynamo. But moving enough mass to change the magnetic field significantly requires enormous energy and should produce other observable effects. Another possibility is that the field is not generated by a traditional dynamo at all. Perhaps Saturn's magnetic field arises from a different mechanism, one we haven't yet understood. Perhaps the perfectly symmetric field and its rapid evolution are clues to a new kind of planetary magnetism. This connects to the magnetic spike Cassini detected in its final moments. A rapidly evolving field generated by unknown mechanisms might produce transient features, spikes, fluctuations, structures that appear and disappear. The final message might be a glimpse of this unknown magnetism, a signature of processes operating in Saturn's interior that we have not yet discovered. Now let me discuss what the scientific community has concluded and what remains unresolved. In the years since Cassini's demise, scientists have analyzed the final data extensively. Papers have been published, conferences have been held, and debates have ensued. Some anomalies have been partially explained. The complex hydrocarbons at high altitude might be transported by unexpectedly vigorous convection or might represent ring material falling into the atmosphere. The magnetic spike might be a reconnection event or some form of atmospheric electrical activity. The particle burst might be related to Saturn's radiation belts interacting with the upper atmosphere in ways we hadn't modeled. But none of these explanations are fully satisfying. Each requires assumptions that are not independently verified. Each stretches existing models to their limits. The temperature drop in the final seconds remains particularly problematic. No conventional explanation has been proposed that accounts for cooling during atmospheric entry. The observation stands as a genuine mystery, a data point that doesn't fit any model. Some scientists have suggested that the temperature sensors were measuring something other than air temperature, perhaps thermal radiation from the spacecraft itself, or some artifact of the entry dynamics. But the sensors were designed to measure atmospheric temperature, and they had been extensively calibrated. If they measured something else, we don't know what. The scientific consensus, to the extent one exists, is that Cassini's final data revealed phenomena at the edge of our understanding. Saturn's atmosphere is more complex, more dynamic, more strange than our models capture. The final message was not an error or an artifact. It was a glimpse of something real that we don't yet understand. This is perhaps the most terrifying aspect of the findings. They are not wrong. They are unexplainable. The data is solid. The interpretation is lacking. Now let me reflect on what this means for our understanding of Saturn and of giant planets generally. Saturn is one of 4 giant planets in our solar system, along with Jupiter, Uranus, and Neptune. We have visited all of them with spacecraft, though none as extensively as Saturn. Cassini's discoveries challenge not just our understanding of Saturn, but our understanding of giant planets as a class. If Saturn's magnetic field violates dynamo theory, what does this mean for our understanding of planetary magnetism? Do other planets have similar anomalies we haven't detected? Is our theory of dynamos fundamentally incomplete? If Saturn's interior is structured differently than expected with a diluted core and fuzzy transitions, what does this mean for our models of planetary formation? Do other giant planets have similar structures? How does this affect our understanding of how planets form and evolve? If Saturn's rings are young, What does this mean for the history of the Saturn system? What catastrophic event created them? Could similar events occur elsewhere? Could rings form and disappear multiple times over a planet's history? Each of Cassini's discoveries opens new questions, new directions for research, new mysteries to explore. The mission answered some questions but raised far more. And the final message, the unexplainable data from the last moments, reminds us that the universe is not obligated to conform to our expectations. Saturn is stranger than we knew. The cosmos is stranger than we knew. And we are only beginning to understand. In part 3, I want to explore the deepest implications of Cassini's final message. What does it mean that a spacecraft's dying transmission contained data we cannot explain? What does this tell us about the limits of our knowledge? And what might we discover when we return to Saturn, as we inevitably must? So we've established what Cassini found in its final moments and placed those findings in the context of its 3-year mission. We've seen how the final anomalies connect to broader mysteries about Saturn, its rings, its moons, its atmosphere, its interior, its magnetic field. We have confronted the unsettling reality that some of what Cassini recorded simply cannot be explained by our current understanding. Now I want to explore the deepest implications. What does it mean when a spacecraft's dying transmission contains data that defies explanation? What does this tell us about the limits of scientific knowledge? And how should we respond to mysteries that resist resolution? Because Cassini's final message is not just a puzzle to be solved. It's a reminder of something profound about our relationship with the universe, the vastness of what we don't know, the strangeness of what awaits discovery, and the humility that genuine inquiry requires. Let me begin by examining what it means to encounter the unexplainable. Science is built on the assumption that the universe is comprehensible. Given enough data, enough analysis, enough theoretical development, we expect to understand what we observe. This assumption has been remarkably successful. We have explained phenomena from the subatomic to the cosmic, from the origin of the universe to the structure of life. But the assumption has limits. Some phenomena resist explanation, not because they are supernatural or beyond physics, but because our current understanding is incomplete. We encounter boundaries, edges of knowledge beyond which our theories fail. Cassini's final data sits at such a boundary. The observations are real, the instruments were functioning, the data is valid. But the explanation eludes us. This is not the first time science has encountered the unexplainable. History is filled with observations that defied contemporary understanding phenomena that seemed impossible until new theories made them comprehensible. The motion of Mercury's orbit couldn't be explained by Newtonian gravity. For decades, astronomers proposed hidden planets, modified calculations, and other fixes. None worked. The explanation came only with Einstein's general relativity, which predicted exactly the observed discrepancy. The stability of atoms couldn't be explained by classical physics. Electrons orbiting nuclei should radiate energy and spiral inward, collapsing atoms in microseconds. The explanation came with quantum mechanics, which revealed that classical concepts don't apply at atomic scales. The cosmic microwave background, the afterglow of the Big Bang, was initially unexplainable. It was discovered by accident and interpreted only later as evidence for a hot, dense early universe. In each case, the unexplainable eventually became explicable, but only through revolutionary advances in understanding. The phenomena didn't change. Our theories did. Cassini's final data might be similar. The observations might seem unexplainable today, but become comprehensible with future theoretical or observational advances. We might be missing something fundamental about planetary atmospheres, about magnetism, about the physics of extreme environments. Or the data might remain unexplainable for a long time. Not every mystery is solved promptly. Some wait decades or centuries for resolution. Some might never be resolved at all. The information needed might be lost. The phenomena might be unrepeatable. The universe might simply withhold its secrets. The honest scientific response is to hold the mystery open, not to force premature explanation, not to dismiss the data as erroneous, not to pretend we understand when we don't, simply to acknowledge, here is something we cannot explain. Here is an edge of knowledge. Here is a reminder that the universe is larger than our theories. Now let me consider what Cassini's final message might be telling us about Saturn specifically. The anomalies in Cassini's final data all relate to Saturn's atmosphere, its composition, its dynamics, its interaction with the magnetic field. Together, they suggest that Saturn's atmosphere is more complex, more active, and more strange than our models capture. Consider what we thought we knew about giant planet atmospheres. Giant planets, Jupiter, Saturn, Uranus, Neptune, are dominated by hydrogen and helium. Their atmospheres are relatively simple, chemically driven by convection from the interior, with weather patterns shaped by rotation and differential heating. This picture is based largely on observations and theory developed for Jupiter, which has been studied more extensively than Saturn. The assumption has been that Saturn is similar, a slightly smaller, slightly colder version of Jupiter, following the same basic physics. But Cassini's discoveries suggest that Saturn might be fundamentally different. The perfectly symmetric magnetic field has no counterpart on Jupiter. Jupiter's field is tilted about 10 degrees from its rotation axis, consistent with dynamo theory. Saturn's field is tilted less than 0.01 degrees, inconsistent with every dynamo model we have. The hexagonal polar vortex has no counterpart on Jupiter. Jupiter's poles have chaotic, swirling storms, but nothing like Saturn's geometric precision. The young rings have no counterpart on Jupiter. Jupiter has faint rings, but they are diffuse and ancient, very different from Saturn's massive, possibly young ring system. Saturn is not simply a smaller Jupiter. It is a different kind of world, following different rules, exhibiting phenomena that don't occur on its larger sibling. This suggests that our understanding of giant planets is more limited than we assumed. We extrapolated from Jupiter to Saturn and were wrong. The physics might be the same, but the outcomes are different perhaps because of Saturn's different size, different internal structure, different distance from the Sun, different evolutionary history. Cassini's final message might be another example of this difference. The anomalies might reflect processes that occur on Saturn, but not on Jupiter processes that our Jupiter-centric models don't capture. What are these processes? We don't know. But the data hints at possibilities. The complex hydrocarbons at high altitude suggest unusual vertical mixing material moving between layers more efficiently than expected. Saturn's atmosphere might be more dynamic, more turbulent, more connected between depths and heights than Jupiter's. The magnetic field spike suggests localized magnetic activity, perhaps reconnection, events, or current systems that don't exist on Jupiter. Saturn's magnetic field, with its strange symmetry and rapid evolution, might produce transient phenomena unlike anything on other planets. The temperature drop in the final seconds suggests an energy sink, something absorbing thermal energy in a region where we expect energy release. This is deeply puzzling, but it might indicate atmospheric chemistry or physics that we haven't considered. These are speculations, not explanations. But they point toward a picture of Saturn as a more dynamic, more complex, and more alien world than we imagined. The final message might be the clearest indication yet of just how strange Saturn really is. Now let me explore what we might learn from future missions to Saturn. Cassini's demise left a void in our exploration of Saturn. No spacecraft currently orbits the planet. No missions are en route. Our only data comes from Earth-based observations and the archive of Cassini's 13 years of measurements. This situation will eventually change. Saturn is too important, too scientifically rich, too mysterious to ignore. Future missions will return, and when they do, they should be designed to address the questions Cassini raised. The first priority is the atmosphere. Cassini's final data came from a single entry trajectory, one path through one region of Saturn's atmosphere at one time. The anomalies might be localized or they might be global. We need more data from more locations. An atmospheric probe mission similar to the Galileo probe that entered Jupiter's atmosphere in 1995 could provide detailed measurements of Saturn's atmospheric composition, structure, and dynamics from multiple entry points. Probes could sample different latitudes, different altitudes, different times in Saturn's day and year. If the anomalies Cassini detected are real atmospheric phenomena, probes should detect them repeatedly. If they were localized events, probes at different locations might find different conditions. Either way, we would learn something. The second priority is the magnetic field. Cassini's measurements revealed that Saturn's magnetic field is unlike any other perfectly symmetric, rapidly evolving, and possibly generated by unknown mechanisms. Understanding this field requires detailed measurements over extended periods. A dedicated magnetometer mission orbiting Saturn for years, sampling the field from multiple altitudes and locations, could map the field's structure and evolution in detail. If the field is changing as fast as Cassini's data suggests, a long-term mission could track these changes and perhaps identify their source. The third priority is the interior. Many of Saturn's mysteries trace back to its interior, the source of the magnetic field, the heat that drives atmospheric dynamics, the structure that shapes the planet's behavior. But Saturn's interior is hidden, inaccessible to direct observation. Seismology offers one approach. Saturn, like the Sun and other stars, might oscillate vibrating in response to internal pressure waves. These oscillations would produce subtle variations in the planet's brightness, shape, or rings. Detecting and analyzing them could reveal the interior structure. Cassini found hints of oscillations in Saturn's rings patterns that might be excited by internal vibrations. A follow-up mission could study these patterns in detail, using them as probes of the deep interior. The fourth priority is the moons. Enceladus and Titan remain among the most scientifically important targets in the solar system. Enceladus's ocean might harbor life. Titan's complex chemistry might offer insights into prebiotic processes. Both deserve dedicated missions. The Dragonfly mission, scheduled to launch in the 2030s, will send a rotorcraft to Titan to explore its surface and chemistry. This is an excellent start. But more missions will be needed, to Enceladus's jets, to Titan seas, to the boundaries between ice and ocean on both worlds. These future missions will not just answer questions, they will raise new ones. Each discovery opens new mysteries. Each answer reveals new puzzles. The exploration of Saturn is not a project with an endpoint, but an ongoing endeavor extending as far into the future as human curiosity persists. Now let me consider what Cassini's final message means for our understanding of the scientific process. Science is often presented as a progression from ignorance to knowledge, a steady march toward truth, with each discovery adding to the edifice of understanding. This picture is not wrong, but it's incomplete. Science is also an encounter with mystery. The more we learn, the more we discover how much we don't know. Each answer reveals new questions. Each solved puzzle exposes deeper puzzles beneath. Cassini's final message embodies this encounter. After 13 years of discovery, after revolutionizing our understanding of Saturn, its rings, and its moons, the spacecraft's dying transmission contained data we cannot explain. This is not a failure of science. It is science working as it should, confronting the unknown, acknowledging the limits of current understanding, pointing toward future directions for inquiry. The temptation is to explain away the anomalies, to force them into existing frameworks, to preserve the illusion that we understand. But this temptation must be resisted. The anomalies are real, our models are incomplete. The honest response is to hold the mystery open. This requires a particular intellectual virtue, something we might call epistemic humility. Not the false humility that denies genuine knowledge, but the true humility that acknowledges the boundaries of that knowledge. We know a great deal about Saturn. Cassini taught us more than we could have imagined before the mission launched. But we don't know everything. The final message reminds us of how much remains to be discovered. This humility is not weakness, but strength. It keeps us curious, keeps us searching, keeps us honest about what we do and don't understand. It is the foundation of genuine scientific progress. Now let me explore what Cassini's legacy means for the broader enterprise of space exploration. Cassini was one of the most successful space missions in history. It returned more data, made more discoveries, and operated longer than its designers had hoped. It transformed our understanding of the Saturn system and demonstrated what dedicated long-term exploration can achieve. But Cassini also demonstrated the limitations of robotic exploration. It could orbit, it could observe, it could sample the environment from a distance, but it couldn't land on Saturn, couldn't drill into Enceladus's ocean, couldn't walk across Titan's surface. The data from Cassini's final plunge illustrates these limitations. The spacecraft descended through Saturn's atmosphere, sampling conditions directly for the first time, and immediately encountered phenomena it couldn't explain. Deeper study would require more sophisticated instruments, more sampling, more time, but Cassini had none of these. It was destroyed within minutes of beginning its direct exploration. Future missions must go further, not just orbit, but land, not just sample, but analyze in depth, not just observe, but manipulate, experiment, test hypotheses directly. This is difficult and expensive. Landing on Titan requires sophisticated entry systems and surface mobility. Penetrating Enceladus's ice requires drilling technology and autonomous operation. Probing Saturn's deep atmosphere requires craft that can survive extreme pressure and temperature, but the science demands it. The mysteries Cassini revealed, the hexagon, the magnetic field, the final anomalies, will not be solved by remote observation alone. They require direct engagement with the phenomena, measurements made in situ, samples returned for analysis. The exploration of Saturn has entered a new phase. The broad survey is complete. The deep investigation must begin. This will take decades, perhaps centuries, but the path is clear and the goal is compelling: to understand as fully as we can this strange and beautiful world. Now let me reflect on what it means that a dying spacecraft sent a message we cannot understand. There is something poignant about Cassini's final moments. A machine built by human hands, launched from Earth, traveling for 7 years to reach Saturn, orbiting for 13 years, making discovery after discovery, and then, in its final minutes, encountering something beyond our comprehension. The spacecraft didn't know it was dying. It had no consciousness, no awareness, no understanding of its situation. It simply did what it was designed to do: collect data and transmit it home. But we know what happened. We received the final transmission, analyzed the data, and confronted the mystery. We are the ones who must make sense of it or acknowledge that we cannot. This is the human condition in microcosm. We build tools to extend our senses, to reach beyond our bodies, to explore places we cannot go ourselves. These tools report back, telling us what they find. And sometimes what they find exceeds our ability to to understand. The universe is not obligated to be comprehensible. It exists independently of our theories, our models, our expectations. It contains phenomena we have not imagined, processes we cannot explain, depths we have not plumbed. Cassini's final message is a reminder of this vast unknown. It is a challenge to our assumptions, an invitation to curiosity, a call to continued exploration. The spacecraft has gone vaporized in Saturn's atmosphere, its atoms dispersed among the clouds. But its data persists, stored in computers on Earth, available for analysis by scientists who haven't yet been born. Someday, perhaps, someone will explain what Cassini found in its final moments. They will develop new theories, make new observations, achieve understanding that we cannot. They will look back at our puzzlement with the gentle condescension of those who know what their predecessors could not know. Or perhaps the mystery will persist. Perhaps Cassini's final message will remain unexplainable, a permanent reminder of the limits of human knowledge, a monument to the strangeness of the universe. Either outcome is acceptable. Science is not about achieving final answers. It's about pursuing understanding as far as we can. The pursuit is the point, and the pursuit continues. Now let me consider what Saturn's mysteries tell us about our place in the cosmos. We are inhabitants of a solar system that contains wonders beyond imagination. Saturn, with its rings and moons and mysteries, is one of these wonders, a world so different from Earth that it might as well be from another universe. And yet, Saturn is here in our cosmic neighborhood, accessible to our spacecraft, within reach of our understanding. It is part of the same solar system that produced Earth, formed from the same primordial cloud of gas and dust, subject to the same physical laws. The differences between Earth and Saturn are immense, but the connections are equally significant. We are made of the same elements, born from the same origin, evolving under the same cosmic rules. This is the paradox of cosmic exploration. The more we explore, the more we find that is strange and unfamiliar. But we also find that the strangeness is comprehensible, built from the same physics, following the same principles, part of the same universe that includes us. Saturn is not a mystery forever beyond our reach. It is a challenge, a world that demands our best efforts to understand, that rewards those efforts with glimpses of its secrets, that continually reveals new depths as our capabilities grow. Cassini's final message is part of this ongoing dialogue between humanity and the cosmos. We send our questions outward. The universe sends answers back, sometimes clear, sometimes cryptic, sometimes utterly baffling. The cryptic answers are not failures, they are invitations. They tell us where to look next, what questions to ask, what assumptions to challenge. They are gifts from a universe that has more to teach than we have yet learned. Now let me conclude with reflections on what Cassini's legacy means for the future. Cassini is gone, but its impact persists. The data it collected will be analyzed for decades. The discoveries it made will shape planetary science for generations. The questions it raised will drive future exploration, but more than data and discoveries, Cassini leaves a legacy of inspiration. It demonstrated that we can explore the outer solar system, that we can sustain missions for decades, that we can make discoveries that transform our understanding. The final message, terrifying, unexplainable, haunting, is part of this legacy. It reminds us that the universe is not exhausted by our current understanding. It challenges us to push further, to explore more deeply, to confront the unknown with courage and curiosity. The next generation of explorers, the scientists, engineers, and astronauts who will design and fly future missions, inherit this challenge. They will pick up where Cassini left off, extending our reach, deepening our knowledge, confronting new mysteries, and someday perhaps they will understand what Cassini found in its final moments. They will explain the anomalies, resolve the puzzles, make sense of the unexplainable, or they will find new mysteries, deeper and stranger than anything Cassini encountered. This is the nature of exploration. The horizon always recedes, always revealing new territory, always offering new wonders. Cassini's final message was terrifying because it reminded us how much we don't know. But it was also magnificent, a testament to human ingenuity, human curiosity, human determination to explore. The spacecraft is gone, but the exploration continues. It continues in the analysis of Cassini's data, in the planning of future missions, in the questions asked by children looking up at Saturn in the night sky. What did Cassini record before it died inside Saturn? Something unexplainable, something that challenges our understanding, something that calls us to continue the journey. The final message was terrifying, but it was also a beginning, the beginning of the next chapter in humanity's exploration of the cosmos. We received the message, now we must respond.